Hello and welcome back to Calculus 1. This is section 3.1, definition of the derivative. But it's going to be all limits, actually. So we are going to tag this together with chapter 2 on the exam. We are going to take lots and lots of limits here. Well, let's first get to that point. So what are we doing now? We're going to take a look at a function f of x, and we're going to locate 2 points, that function, and I'm going to connect those 2 points, this blue line. This is a linear line that will actually go on forever, you know. It's the line that cuts through the function, through these 2 points, call them A and B. And we can find the slope for that line, and we'll call that m secant, because the line is called a secant line, because in Greek that means to cut. So slope of the secant line must be f of, well, let's put y2 minus y1 over x2 minus x1, and then those are the points from here. So let's write it one more time with a and b. So yb minus ya over xb minus xa. And we know that there is, for point A, xaya, and for point B, xbyb. So we can find the slope of this line. Now what I want to do is I want to let A approach B. So in a new, let's draw a new one. So in this next iteration, and I'm going to exaggerate this a little bit like that. That's good enough. Let's see. Let's say it's good. So I'm going to have my 2 points here. And I'm going to connect again the secant. I'm not going to extend it infinitely, we all understand. And that's where the m secant is. And now I'm going to let this point A travel towards B. So at some point over here, it's going to be at the location A1, location A2, location A3, and so on. And each one of these will have its own secant line connecting the new point, the new location where the point is, to the point B. So what's happening here is that the point A is traveling. So let A approach B. Now we know that the notation is A goes to B with the arrow, right, under the limit. So it's calculus, it's motion, right? Things are changing. So we're still in the realm of calculus. And every time this point gets closer to B, the slope of the line changes. So what you see here is that the slope starts changing as soon as A starts moving from A towards B. Now, we have no issues using algebra, which is the formula that you can see above in blue. We have no issues using algebra to actually get every one of those slopes. There are infinitely many of them because there are infinitely many points in between A and B. But we have issue at one point. We have issue when A gets to B. when they become the same point. When A passes B, life is still good, because again, you have two distinct points, and when you do the subtraction of x values in the denominator, you're not getting 0. But you see that when A is equal to B, YB minus YA, because they're the same height, becomes 0, and XB minus XA, because they're the same x location, becomes 0. So actually your calculation for the slope at that point becomes 0 over 0, which is no bueno, right? Can't compute. So we are able to use algebra to compute every single slope when A is at any location before B or after B, which is infinitely many locations. The only time we are not able to use algebra is when A and B end up at the same point. But I want to say the awesome part is that even though we are not able to use algebra to compute the slope there, the line and the slope still exist. And that line is a very special line. So you have infinitely many of these blue lines that you can use algebra to solve, but there will be only one red line like this that goes through B, and I'll draw that later in many different locations, which cannot be computed with algebra, and for that one we need calculus. This red line is called tangent line. And this line is the focus of Calculus 1. The entire Calc 1, well, not that much chapter 5, but the purpose of Calculus 1 is to learn about the change. So we had to learn limits so we can do this section. And then the rest of the course is the tangent line. Tangent line measures the change at the point. So tangent line measures the change at the point. What point? X, Y. So now, you're looking at this, and I say, what's the big deal? It's a huge deal. This is your Calculus 1, this red line. That's Calculus 1. And then a little bit, five sections in chapter 5 for integration. So now, how do we calculate this line? Well, the concept should be clear. You have infinitely many lines that you can compute before the red line. You have infinitely many blue lines after. Which concept deals with that? Which concept doesn't compute function value? It computes infinitely many function values before and after the point, and then says, that's the point you want. Limits. So what is the crudest definition you can get for the slope of the tangent line? Anyone? Yeah, but yeah. So what should we write? My pen stops working. So m tangent is equal to the limit of just just my pen. My pen decided to die at the crucial moment, and it just works partially actually now. So annoying when it disconnects. There we go. So hopefully it works now. Yep. So the point. So the crudest definition is that m tangent is equal to the limit as a goes to b for m secant. Now we'll never use this, right, in any calculations, but that's the concept-wise, theory-wise, that's the point we are making for Calc 1. Now we talk about the details, right? So what are the details? The details are that m tangent is equal to the limit when a goes to b, m secant, yes, of yb minus ya over xb minus xa. We also know that y equals f of x. Now we're going to switch to black and I'll just use the red one for the important stuff. So m tangent is the limit when xa approaches xb for f of xb minus f of xa divided by xb minus xa. Very little changed. I'm now using x locations for the approach because we know we approach on the x-axis, right, left and right. And I use the pre-calculus notion that y is f of x, so I'm replacing y, but it's yb. So I can write xa, ya, or I can write xa, f of xa, because f of xa is ya. So I'm just replacing these things in. So this formula is the same as that one, except it has a function notation in it. And now when you look at this, right, you have your you have the way to compute the tangent line. We are not learning new type of a limit. It's 2.3, which you already know, that solves these problems. You will be rationalizing or adding fractions or something, right? So 2.3 is all you need to solve these problems. We are learning the concept now of what these things do and what they mean. And the mechanics of the problem is in 2.3. All right, so now let's make this calculation friendly. I'm going to change the picture a little bit so that we can, in this picture, I'm going to make my point A stationary. So that's xa. And I'm going to make point B the one that travels towards A. So we know there's initial one, and then there are all the other ones that exist, and we know that our goal is to reach that one, which is going to be the tangent line. So all of these over here are the new iterations of B as it travels along the function to collide and reach A and then create that new line. So now what do I have? If I'm to use the same thing, we see that this formula that I wrote up there is just going to be flipped in terms of A's and B's, but it's the same formula. So m tangent is going to be limit as xb approaches xa, because xa is the one that is stationary. And then I will have f of xa minus, sorry, f of xb minus f of xa, xb minus xa. I'm actually going to box this as the, too much. We'll keep this one for the actual formula. So now we can see this working. You pick any b value, it's going to be b minus a over b minus a. So b is going to travel along the function f of x. So this line is f of x. It's x-axis, y-axis. And it's going to go all the way around. Now what's going to happen here? Well, to make calculations much easier, we are going to define age as xb minus xa. We actually have two motivations for this. First motivation is obvious. It's right there. That's no questions. But then there is a hidden one which says, can we make this more pleasant? And the answer is yes. If you are to subtract xa on both sides, what happens is the left-hand side becomes xb minus xa, that, and then this one becomes 0. It's much nicer to have some new variable age go to 0 than to write xb minus xa every time you have this. So we are technically plugging that substitution in. So if you want to think of this as a substitution, go ahead, because it is. And what I'm going to do now is I'm going to plug that in. So now m tangent becomes the limit of, I'll write it one more time, xb minus xa goes to 0 of f of xb minus f of xa. I constantly want to write a lowercase a, xb minus xa, and then I'm just going to point out to the two places where we substitute, and also I'll do the dashed line right there, because we are going to eliminate all xb's. Because you never know where xb is, right? It travels, it moves. So now what m tangent looks like? It looks like the limit of age goes to 0, denominator becomes age. Now the dashed line here is, if you solve the equation, you see that xb is xa plus age. So f of xa plus age minus f of x. Do you recognize this? It's a difference quotient from your Calc 1, or from your pre-Calc 1. This is the one that gets the fat box. The slope of the tangent line. Oh, I'm missing xa, guys. The last over here, xa. There we go. So all of this was one big substitution. Try to fit everything in, I can't. So we started with what we developed this from algebra. This is an upgrade. It is not a new concept out of blue. It's an upgrade from algebra, basic slope, y2 minus y1 over x2 minus x1. We started with the algebra concept, and then we added a little bit of calculus to get this. So as the point B moves, the xb keeps changing its value to eventually collide and become xa at the same point. At that point, algebra cannot compute the slope any longer because you have 0 over 0. Then we said, okay, cool. We have infinitely many lines that I can compute before that happens. When B passes on the other side, infinitely many lines that I can compute afterwards. I know how to deal with this. It's limited. So the slope of the secant line, we're going to say slope of the tangent line is going to be limit of the secant line. We write the slope of the secant line, which is y2 minus y1 over x2 minus x1, except we just use f of x instead of y. And then we recognize the form xb minus xa and say minus xa on both sides, which gives us this formula here. Since we have xb minus xa, we put a substitution, just to call it h because we're lazy. And it becomes x minus b, that's h, goes to 0. xb minus xa, h again. And now we don't want any xb's anymore because we never know what xb is. It keeps changing, right? It used to be 3, let's say, and it was 2.9 and 2.8 and whatever. But there's infinitely many, right? So we want to eliminate that xb because xa is the one that is fixed. That one stays. We know at all times what the coordinates here are. xa, yb, sorry. xa, ya. So all of this, now we eliminate all xb's and we get into the equation here which computes the slope. So what I have now is the point whose location I always know. Let's say that this point over here is 2, 3. This xa is 2 all the time. It doesn't change, it's a fixed point. And then the b. So now I can compute this. You give me the function, I just compile all of this, and just spit out the answer. You actually did this for your homework in 2, 3. Someone told you what it was, but you did it. You already know how to compute these problems. And now we're just giving it a name and giving it the meaning, the concept behind the whole thing. Good time. So, find the slope of the tangent line at x equals 3 for function y equals negative 2x squared plus x minus 2, whatever. Doesn't matter. You have the formula up there. All you need to do is to plug everything in and compute limit using 2.3. So we start by writing that the slope of the tangent line is going to be equal to the limit as h goes to 0. That's the standard. It's going to be divided by h. That's standard. We're going to have f of 3 plus h minus f of 3. So you are memorizing the formula. You should already know it. It's a quotient, difference quotient. And now with using function composition and plugging in values, you're getting this. So m tangent here as the limit of h goes to 0, f of x plus h minus f of, sorry, the xa's, okay, over h. So this is the boss for today. And we are calculating this at x equals 3. That's our fixed point. So this becomes 3 and this becomes 3. That's the x coordinate of the point. So now, all I need to do is to put this together using pre-calculus and then use 2.3 to solve it. In pre-calculus, we learned that the function composition is, first of all, let's do the easy one. Let me write the function first. So f of x is negative 2x squared plus x minus 2. So how much is f of 3? Negative 17, clearly, right? So we have negative 2 times 9 is negative 18. Oh, I forgot to plug 3 here. So negative 18 plus 1 is negative 17. Awesome. And how much is f of x 3 plus h? Well, it's negative 2, 3 plus h squared, plus 3 plus h minus 2. You have to figure out this algebra. So it's negative 2 times 9 plus 6h plus h squared. And then you have plus 3 plus h minus 2. That's going to be negative 18 minus 12h minus 2h squared. I'm going to combine these two into plus 1 plus h. And then the final thing here, I'm going to start with negative 2h squared. That's the largest exponent. And then minus 12h plus h is minus 11h. And then minus 18 plus 1 is negative 17. I'm making these building blocks. And all I need to do now is to swap it. I don't know if you're into fixing computers or fixing cars or fixing whatever, just swap the component, right? So instead of this, f of 3 plus h, I have this mess. Instead of minus f of 3, I have negative 17. I just swap those things in. Just plug them in. I have the pieces. I plug them in now. So what's m tangent? It's the limit. H goes to 0. Instead of f of x plus h, I have minus 2h squared minus 11h minus 17 minus, and then I have negative 17 instead of minus f of 3 divided by h. How do you solve this limit? So yeah, so these guys cancel because negative 17 plus 17 is 0. Now you see that you can factor h and cancel, and you can get the limit. So kick h out. I know you can kick negative h, but just kick h because that's the only thing you need to cancel. So now h dies off. And we have limit. H goes to 0. Negative 2h minus 11. So what happens now? What happens as h goes to 0? The answer is negative 11. So m tangent is equal to negative 11. That's the answer. I'm going to repeat the whole problem from the beginning. Make sure everyone is on board. But this is how you find the slope of the tangent line. The hardest possible way. Or should I say the most annoying possible way. Find the slope of the tangent line at the point x equals 3 for function y equals over here stuff. So we are going to put our difference quotient together, take the limit, and that will give us the slope of the tangent line. So slope of the tangent line works out to be, we plug in 3 for those xa's, and we have f of 3 plus h minus f of 3 divided by h. Now, we have the function. We know we have to find f of 3, because we need f of 3 to plug in, and we did eventually. That's f of 3. We computed it was negative 17. I don't know if you can follow all these circles, but we use 3 in the function because we had to, right? And all of these circles are related. That's all f of 3 related. Then I chase the other one, except the other one is not arithmetic calculation. The other one is algebra calculation, which is this. So you are replacing x with 3 plus h. So if you compare that, there is x squared, there is 3 plus h squared, there is plus x, there is 3 plus h. So these all work together at the same time. If I'm replacing x with 3, I replace every x by 3. If I'm replacing x with 3 plus h, I'm replacing every x with 3 plus h. Do we all see that? Because later, that's going to be something else. It's not just going to be 3 plus h. Once I have all of the building blocks, I like to call them building blocks. Once I have all the building blocks, I will plug this way. Instead of this, I have this, which is here. Instead of this, I have that, which is here. And from that point on, work out arithmetic. You see that 7 minus 17 becomes plus 17. Those 17s drop. Factor out h. Cancel off h. You're left with this. 2h goes to 0 because h goes to 0. 2 times 0 is 0. The answer is negative 11. Bueno. I'm actually alone in this classroom. You can't tell. The screen can't tell. I'm actually talking to 4 walls now. All right. But you know what? I just realized that I actually didn't want to find the tangent line at x equals 3. I wanted to find it at x equals 5, so we have to do this all over again. And I would really appreciate if you would do that for me. Thank you. We have the same function, same x squared. So this is almost like you just swap all 3's with 5's and just do it, right? That's what I wanted. I wanted a 5. It's a good practice. I mean, the answer will be negative 19, but you know.
Let's move here to there.
What?
Let's stop the journey not to go to the engineering.
Exactly. Enjoy. Hopefully that negative 19 pops out. I'll be very sorry. I was wrong to do all this. How's it going? Negative 19? You all have negative 19?
Yeah.
I want to do negative.
All right, so negative 19 it is. You know what I'm thinking? How about at negative 4? What's the